Yes, my great pleasure to introduce today's speaker of our seminar, Paul Hand, Professor Paul Hand. He received in 2009 his PhD from Curran Institute in Mathematical Sciences at New York University, where he also received a prize for his outstanding PhD thesis. He then was a postdoc and an applied math instructor at MIT. He also was an assistant professor computational and applied mathematics at Rice University, and now is a assistant professor at mathematics and computer science at Northeastern University in Boston. So his current research focuses on the theory and algorithms for machine learning in the context of vision and imaging, and it's a great pleasure to have Paul Hand here today.
All right, thank you so much for the invitation. It's a pleasure to be here. So I want to tell you about some interesting recent developments as it lies at the intersection of applied mathematics with a lot of inspiration by what's happening in machine learning and deep learning in particular. And this is going to be a talk about signal recovery using deep generative neural networks as image priors. And so I'll explain a bit more about what that all means. Right. So first, right. So we're going to talk about signal recovery, where this lives in the framework of inverse problems, and so then here there are a variety of inverse problems that are very interesting, to various scientific and non-scientific disciplines, and they have this flavor. Right. There is an image or other signal like audio or whatever. Let's call that x naught. And then you're going to have access to perturbed or distorted or few measurements of x naught. So maybe you have a noisy version of x naught and your goal is to denoise it. Maybe you have some missing pixels of x naught. Your goal is to in-paint those pixels. Or perhaps you have a low resolution version and you're trying to super resolve the image. There are also other problems that are a bit more general. So something called compressed sensing, which we'll talk about in a bit, where you might have somewhat generic linear measurements of your image, but you have many fewer measurements than the dimensionality of your image. And then there are nonlinear versions of this, which we'll also talk about, such as phase retrieval, where you might have only the amplitude of linear measurements of your image. And your goal is to recover the image from those measurements. So in all of these cases, right, so we have this image x naught, we have some measurements, linear or nonlinear, which we're going to tuck into, say, phi of x naught. The goal is, given phi of x naught, find x naught. So just to make this really concrete, right, one of the major applications of this is in compressed sensing, for which a major application of that is magnetic resonance imaging. And here, just pictorially, you could have, like, here's an MRI machine. Then we may know for if you've had an MRI taken before that they take a really long time, right? And so I've actually had when I was a grad student at NYU, I decided to donate an MRI of my heart to a study so they could have a three-dimensional model of heart. And so I sat in that MRI machine for about an hour and a half before I literally went crazy and started asking the doctor if they were still there or whether they just abandoned me in the machine. And so the point is that it's, these machines are very slow for various physical reasons. And so it's important to speed them up. Now, the actual way you speed them up is not by making the parts move faster. It's in part by subsampling, just not collecting as much data. Right, so what you see in the middle here is data that comes from as the output from one of these machines, and you can see that there are a bunch of columns that this data lives in, but some of those columns are missing. So here, this is a visualization of the Fourier transform of the signal, that the true image of what's in the machine. And now the question is, how can you recover a beautiful image of the MRI of your knee or your brain or whatever from as few measurements as possible, right? And indeed, this is of significant societal impact. But there are a whole bunch of other inverse problems out there, as well. So I mean, there the similar ideas that we'll talk about today will apply, say, like in this right setting where of electron microscopy, where you want to like visualize the shape of very small molecules. In the top left, these are like this comes from the world of like seismic imaging, where you're trying to estimate the material parameters of the Earth, like from various data where you might have machines that like bang on the Earth, and then you detect where are the echoes of those oscillations, and try to infer the shape of that. And in the bottom left, this is an illustration of the cocktail party problem, where you have a lot of separate sources of, say, like different people speaking, and you have perhaps one receiver, i.e. your ears, and you want to disentangle, what did this person say versus what did that person say, right? So this is, I mean, it's a underdetermined problem because you're really only hearing, you have one source and all the signals are jumbled together. So you have like fewer measurements, if you will, than the true dimensionality of your signals. And so there's a whole variety of inverse problems that are out there, and we can remind ourselves like what are like the classical, the now classical approaches to solving these inverse problems. Like what do they look like? Perhaps like the most dominant now classical approach, the most dominant method of the last like 20 years has been to exploit the idea of sparsity. And so, for example, this is now this famous a famous representation of signals. So the top left panel of this figure, right, is the image of a boat, and the bottom left panel shows like the amplitude of the coefficients in a wavelet basis for that image. And so you can see that there's a relatively few large amplitude coefficients, and then there's a long tail. Right, so you can like cut off that tail, reconstruct the image. You get this image on the bottom right, and you can see indeed that it's a reasonable approximation of the image on the top left, but it's been compressed. Right, and so this gets at the idea that right, like natural images are approximately sparse in a wavelet basis. This has been a dominant theme of the last several decades in applied mathematics and in signal processing. So when we turn this into a question about inverse problems, so let's say you're given some forward model. I called it phi on the previous slide, but in this slide it's written out in words as forward model. You might want to minimize the L2 norm of your observations from the forward model applied to some image X, and you might search for sparse X. So here X could be best viewed as like the coefficients of your image in the wavelet domain. All right, so this is this this now classical sparsity perspective, and when we think about like how to actually like do this sparse optimization, there's this famous relaxation, which is that instead of minimizing L0, minimize L1, right? So on the left, what we see is the natural formulation based on the intuition that natural images are sparse with respect to the wavelet basis. So here we have our measurements phi of x naught. So we would optimize over images X and constrain ourselves so that the forward model applied to X agrees with our data or approximately agrees with our data. And we want to minimize the L0 norm of X. So that means the number of non-zero coefficients of X. So doing this is NP hard. And so there is this standard relaxation to instead minimize the L1 norm of X subject to these constraints. Right? And so this has been known for many decades. And has given rise to one of the like celebrated and famous results in the field of compressed sensing, is due to Candace Romberg and Tao, and then also due to David Donahoe. And this result, I want to talk about right now, because what we're going to do in the rest of the talk is do something somewhat as similar as we can in the more modern paradigm, right? So this result is about recovering a sparse vector given random Gaussian measurements. And the question is, how many measurements do I need in order to recover my sparse vector? Now, the answer to this question is, well, you need a number of measurements that's roughly proportional to the sparsity level of your signal. Right? So if you have a k-sparse vector x naught, and it lives in n-dimensional space, and so n you should think of as large, like number of pixels, and k you should think of as small, how the ability for sparsity to compress that image. So then this famous result says that if you have measurement number that's on the order of k log n, then with high probability, you can recover your image x naught by solving this linear program by doing this L1 optimization. Right? So this is like the basis of the field of compressed sensing. And so this has spawned many very very interesting works from many very good scientists over the last several decades. Now, so this all is great, right? This result is optimal in the sense that like you couldn't hope for better scaling in k. So technically, it's like m needs to be like k log n over k, but let's ignore that log factor for now. The point is like this scales optimally in k. Right. So here's now where the story sort of gets tricky. Is that sparsity so far has failed in nonlinear inverse problems such as compressive phase retrieval. So we're jumping gears for a second. Before we were talking about linear signal recovery, right? If we go back, right? So we had this like a of x equals a of x naught, or phi of x equals phi of x naught for linear phi. Here, let's look at a nonlinear version. So in this problem, you have some signal x naught, and so it's this tall vector in the middle. You have some like measurement matrix A, which has m, say generic random Gaussian measurements of x naught, and then you're only given access to the absolute value of these measurements, right? So your system is absolute value of a x naught equals b, and you want to find x naught. Right? So if there was no absolute value, this would be just compressed sensing, and the standard theory that we just mentioned would apply. But here in this problem, there is no known computationally efficient algorithm that can solve this. So for example, if x naught is s sparse, then you would expect to be able to solve this with O of s generic measurements, but no one knows how to do this. Right? There are various methods out there which, like, if you really tune the nature of A so that it's of an exact structure with the measurements have a very precise structure, then you can do this with O of S measurements. But in general, for generic A, this is an open problem. Right. Now, I mean, since the rest of this talk is largely going to be about this open problem, I want to actually view this problem a bit more broadly, right? So if you talk to someone about, say, the sparse phase retrieval problem, right, that would be what's written down on the bottom of the slide. Basically, can you build an algorithm that can recover an S sparse signal from O of S generic phaseless linear measurements? But when we ask ourselves, like, why do we care about the sparse phase retrieval problem? The reason is because, well, what we really care about is compressive phase retrieval, right? Like we have some image, we have some measurements of this image. They're usually like Fourier modes based on the physics. And then our goal is to recover that image with very few measurements. So we can exploit the structure of this image in order to do that. But we don't have to exploit it via sparsity. Right, so one of my the big comments about the sparse phase retrieval problem is that while it is interesting and hard, it's not exactly the problem that we really need solved. Right, the problem that we need solved is that of compressive phase retrieval. How do I exploit the structure of a signal or image x naught in order to recover it from phaseless linear measurements?
Hi, Paul. Sorry, there's a question in the chat from Tim. So what is the optimization model for sparse phase retrieval?
Well, I will get to that on the next slide. Very good question. So here, let's zoom in. So not only is there no known efficient algorithm, when you do some natural things, they actually even like provably fail. So this can go away toward addressing that questions. So there was this famous approach called phase lift, which came out, I guess many years ago now. And so it viewed phase retrieval through a matrix recovery problem using something called lifting, right? So the idea here was, instead of looking for a signal x, which you have quadratic measurements on, look for a matrix, capital X, which roughly is like little x transpose. And then now your quadratic measurements are linear measurements on this matrix, capital X, right? And so there, you could then write down this very natural formulation, right? So your matrix X should be positive semi-definite because you're actually looking for it to be of the form little x transpose. It needs to agree with your measurements. Those are what's written here in this middle line. And then now we can talk about what else do you want? Well, you want it to be sparse. So why don't you penalize the L1 norm of matrix X, and sure, penalize the trace of X2. Maybe you don't, maybe you need it, maybe you don't need it. But let's leave it there because that was part of the original phase lift method. And so unfortunately, this method doesn't work. And what I mean by that is, so there's this theorem by Xiaodong Li and Vlad Voroninski back in 2012, where they said that, like, suppose you did this for some x naught that is S sparse, then if there was a lambda for which the true solution actually minimized this matrix completion problem, then M would have to be big O of S squared. Right? And so indeed, that is not the optimal sample complexity we're looking for. We want M to scale like S. Right? So morally speaking, what's happened is, once we lifted this from to a matrix problem, now our S sparse solution became S squared sparse. And so now imposing sparsity only gets us optimality in that sense of S squared. Right? And that's not good enough. So now to the question of, are there, like, what is the right formulation? Well, I think that is up for debate. Like you're free to formulate the problem like however you want. Like, this is one such formulation. There are other formulations, like there are linear programs that people have studied. There's just straight up non-convex optimization that people have studied. But in all of these approaches, everyone's stuck at the same barrier, which is that no one can beat O of S squared. Now that said, there's a bit more nuance to it. There are several papers out there now that say that if you can give me an approximate solution, then I only need O of S measurements in order to refine it to the exact solution. But now, how do I get that approximate solution? The best known methods for getting the approximate solution are O of S squared. Right? So we've reduced this problem to being one of just initialization, but that might be challenging. There's actually reasons to believe that this problem might be fundamentally hard. Like there's a very closely related problem called Sparse Pca, where you are also trying to find like a matrix that is low rank and sparse, and that explains like particular data in a particular way. And then there's this famous paper by Quentin Bertet and Philippe Rigolet, which sort of reduced that problem from planted clique, which is conjectured to be NP hard. And so there's reason to believe that it might not even be possible to solve this, like sparse phase retrieval without making fundamental advances to the field of theoretical computer science. And so as a very applied person, then I kind of shy away once that happens.
Sorry, Paul, there was another question just to clarify. The L1 norm of X now here is the L1 norm of the vectorized X, or the
Yes.
nuclear norm, the L1 norm. Okay.
Yeah. So this is like literally the L1 norm of the vectorized X.
Yes.
Is the point
okay.
being, so the nuclear norm that would penalize rank, but since the matrix is PSD, the nuclear norm is the trace, and so that's really what the first term's doing. Yeah. So just to to back up for a second, like the challenge here, and one of the the things that sparsity has generally failed at is it's generally been difficult to simultaneously enforce different notions of structure. Right, so here, right, we're looking in this problem, we're looking for a matrix that is low rank and sparse, right? So this trace of X term, that's promoting low rankness. The second term is promoting sparsity. So it's easy to get low rank, but then you're not optimal sample complexity. It's easy to get sparse, but it's not optimal sample complexity because it's sparse in the matrix sense and not in the vector sense. And so how do we impose these priors simultaneously at the same time? Okay, so this is all setting the stage for like the sparsity just not being a tool that we can mathematically exploit for nonlinear inverse problems, even though it is a tool that we can and have successfully exploited for linear inverse problems. So I want to point out another critique of the sparsity prior, right? And that is that it's not tight. So I mean, what's shown here. So an image on the left, this is a shark, and you can take this, you can compute its wavelet coefficients, you can perturb those, and then recombine the image, and you see the images on the right. So if we believed that images were sparse in the natural in the wavelet basis, then well, both of these images are equally sparse, and so then this view of images, like it leaves a lot on the table. It's over inclusive of unnatural things. Now, I mean, to be fair, of course, we all know that like the best model for natural images isn't literally sparsity in the wavelet basis. There's like model-based compressed sensing. You can say the fact that this wavelet coefficient there now means it's more likely that these other wavelet coefficients there. But nonetheless, the point is made that it itself is an over-inclusive, not tight prior. If we can tighten it, then we may be able to do better. All right. So any questions before we move on? Because now we're going to enter into like the deep learning, machine learning realm.
I just had one quick question, if I may, about the SDP model. So how do you, I mean, the idea is that you're going to have an SDP matrix, but if it's not rank 1, I mean, then it's not little x transpose. I mean, it's still an x transpose, but that doesn't, it's not the vector thing, right?
Yeah.
But so what is it then if it's not rank 1?
Well, so for this program to be successful, it would need to hand you a rank 1 solution.
Yeah, but it's not enforced anywhere.
Right.
It's
so
promoted,
yeah, so let's look at it in the case without sparsity. So shall we say the plain phase lift case? So just remove this L1 norm of the vectorization of X. So that's now this method called phase lift. Then it's been proven that if M is on the order of the dimensionality n up to log factors, then there is a unique solution to this, and that unique solution is exactly rank 1, and it's exactly what you're looking for. Right, so you basically get it for free because in a sense the PSD, right, it's a cone, right, it's sort of pointy in a certain sense. So these linear measurements are now affine like planes that then like only intersect like that pointy edge at an exact at the exact rank 1 solution you're looking for.
Okay, and in terms of scalability, I mean, you still have like X is still n by n, right?
Yeah, so this method, right, it's not a very practical method because your n dimensional problem, keep in mind n is like the number of pixels in your image, so that could be hundreds of thousands. Exactly. So then X is an n by n image, and then matrix operations are very expensive, and so you can't afford to do this in reality.
Yeah.
But remember, our goal here was not to present a sparse phase retrieval method. There's empirically successful. The goal was to just understand, could one do sparse phase retrieval using that tool, no matter how expensive it is? And the answer in that case is no.
Okay, thanks, great.
All right. So okay, so we see that like sparsity is not a tight priors. There's some slack. It's over inclusive of some unnatural images. So what could we do instead? So now enters the modern like AI deep learning regime. So here's a article from the New York Times in early 2018, how AI cat and mouse game generates believable fake photos. And here, these are something called generative models. And generative models have been trained to output synthetic, photorealistic, high-resolution, natural images of human faces. So that is to say, these models like output like this this woman, and maybe you can't tell that this is entirely a synthetic person. Here's just a full face, and sure, there are some artifacts in the image, but this is the state of the art as of 2017. This looks like a real person. But this is not an actual real person. This is a randomly generated output from a trained neural network. And the state of the art has gotten actually like significantly better than this now. If you want a fun a fun viewing on YouTube, you can Google an hour of imaginary celebrities, and then there's a video which shows like the same model that produced this face. It's just an hour-long video of other outputs on that model. And in that video, there's sort of like a continuous deformation of a latent representation. This model then maps that latent representation to natural images. And you can see that these human faces like continuously morph from one into the other. So you can morph in and out of lighting and like pose and like hair color, hairstyle, gender, whether they're wearing glasses or not, right? All these like features of variation that occur in natural images of people are in that outputs of that model. So I encourage you to look up an hour of imaginary celebrities and follow up work from that. Right, so these models, right, they came trained from data, right? So someone collected a whole bunch of images of faces, in this case of celebrities, and then they were thrown at this model, and then the model was told to generate additional faces that look like those faces. Of course, there's nothing special about faces, so you can sample from any variety of complex signal classes. There's basically, if you have the data, you can do it. So there's a bunch of data sets in computer science about photographs of bedrooms, and so you can create generative models of those, or of course, MRI scans, biological cells, fingerprints, you name it. If you have the data for it, you can train a deep generative model to output synthetic new samples of that. So I know this is this is applied math venue. So let's bring back in the math. Right, so what is a deep generative model? Well, generative modeling is the problem where you're given access to a distribution. For example, you're given samples of that distribution. You want to be able to generate new samples, right? And so one way of doing generative modeling is through using neural networks. And so here, this might go as follows. Like you have what's shown on the left is a neural network architecture. It takes as input some, let's say, low dimensional latent code. And then it as output gives you an image of a face. And so then here on the right, you see a whole bunch of images of faces. Right? So again, you have samples in Rn, your image space, from some distribution pi naught. Think of that as the distribution of faces. And your goal is to learn pi naught. Now, you don't have to learn the PDF of pi naught. You just need to learn pi naught enough to sample new elements from it. So then some generative models work as follows. They're going to model pi naught as some function g of z, where z is just a randomly generated standard normal in low dimensional space k. Right, so g is now mapped from rk to rn. K is rk is the low dimensional space for your latent code, and then the output of this is an image. So here, what this is doing is, in a sense, it's compressing the distribution of natural images to be in a k-dimensional space. And it's doing like, and then G is this like highly nonlinear decompression, decoding from those codes. All right, so there's a whole field in machine learning and deep learning about how to do generative modeling well. There's a whole variety of tools. So what I just want to show is just a visualization of what these sorts of things are doing, right? Just to make sure it's clear, right? So in the left, or sort of this middle column labeled data space, think of this as individual images. Like each data point, suppose that is an image. This shows, you know, a two-modal distribution. And so then your generative model is going to live in latent space. It's going to be, say, samples of some Gaussian. And you might want to do the generation problem of like, given Z, generate the image. Or you might say, given an image, do an inference problem. Like, what is the latent code that represents to that image? All right, so these are how these work. But let's go back to, you know, this talk was about inverse problems. So how do we use these for inverse problems? Well, remember, these are priors for natural images. We're trying to replace the sparsity prior conceptually with these generative models. Right, so step one is train a generative model to output your signal class. So what this means is you might have, say, random noise that's like piped into this neural network, and then out comes, you know, these synthetic pictures from the domain of interest that you have, like flowers or MRIs or whatever. And now, when you're solving your inverse problem, you can directly optimize over the range of such a model. Right, so remember, we have data called phi of x naught. We have candidate images that are now modeled as being in the range of G. So G of Z is some image that corresponds to latent code Z. So phi of G of Z are the measurements you would have gotten if that were indeed the image. And so now you penalize the difference here. So this is this two-step process. Step one, learn a generative model for your data. So if you're working with MRI images, then train a model that can like freely generate the sample from the distribution of MRI images. Now use it as in a direct optimization for inversion. All right, so now, I mean, we can think about, like, originally we'd viewed images as sparse on the wavelet basis. Now this perspective is saying view images as being objects in the range of this trained generative model. And then you can search over that directly, right? So roughly speaking, this can be visualized as follows. Like, you have some image x naught, you have measurements of it, ax naught. So then you're trying to find a z naught such that if you pump it through this generative model G, you get x naught back, right? And so you can do this by solving this non-convex optimization problem. This was proposed by this famous Bora et al. Paper from University of Texas at Austin. All right, so this is what you do in compressed sensing. You know, this talk really is about the nonlinear version, so about like phase retrieval, but you can do a similar thing here, right? So here you're given x, like you have some image x naught. Your measurements are absolute value of ax naught. You're trying to find the z naught that corresponds to the image x naught, which is g of x naught, g of z naught. Right, so again, you're finding the latent code such that the output of your generative model agrees with the data that you have. And you can do this by you know, also a non-convex optimization problem. So penalize the square distance between the absolute value of a of g of z and a of x naught. Okay, so this is now a non-convex approach to phase retrieval, to compressive phase retrieval using a deep generative prior. Now I want to show you first a geometric picture of what's going on, just to make this concrete, right? So let's consider like what we're showing. Like, think of the ambient space here as all images, but not all images are interesting, right? Most images are static. So then there's a manifold of interesting images, of natural images, things that could have been taken by a photograph or an MRI machine or whatever. And so that's this manifold. So then now you might have some subclass of that that is interesting to you, like maybe MRI images is a subset of natural images, or this category of pathologies is a subset of MRI images, or whatever. So there's some low dimensional manifold in image space that models your class of natural signals. Let's say here's an image of a train, that maybe that's the image that you're trying to recover. Now you have measurements, and so then those measurements, you're going to have fewer of them than the dimensionality of your image. Otherwise, there would be nothing to do. And so then you're looking for the intersection of this line, or this like space, affine space of images consistent with your measurements. You want the intersection of that with your natural signal class. So the power of these generative priors is that they can directly learn the manifold of natural images, right? And this is in strong contrast to a sparsity prior, right, which views your natural signal as belonging in the union of combinatorially many subspaces, linear spaces, right? So from this perspective, like, yeah, it's tighter because it's literally learning a nonlinear manifold that can actually like fit the nooks and crannies of the image class that you're trying to model. Okay, so I do want to get to this this theorem that we proved about this, and so what we wanted to do was prove a result that's very much like the the Candes-Rambek Tau or Donahoe-based results for compressive sensing, right? We want to show that you can succeed at compressive phase retrieval with measurement sample complexity proportional to the dimensionality of your, like the true dimensionality of your signal class, right? So I did this work with this very talented grad student, Oscar Leong, and Vlad Voroninski, and it went as follows, right? So suppose you have measurements that are given as Gaussian, so that we're like in compressed sensing in that sense. So we have random measurements. Then suppose your generative model has itself random weights, and each layer of the neural network grows sufficiently fast. So this is to say, you'll remember back to this picture, this picture here, where you can see like the size of each layer, like can be growing. So like abstracting that more generally, basically each layer needs to be bigger, wider than the layer before it. So we're studying a case where the generative model is a random function, a random neural network, where each layer size grows by a certain amount. And so then what we showed was that if the number of measurements is proportional to at least k up to logarithmic factors, then the non-convex optimization objective that we wrote down, it has a strict descent direction everywhere except around a ball around the global optimizer, and this one spurious point in latent space, which is a reflection of that. And so what this says is, if you optimize this objective in Z, then you either find your global minimum that you're looking for, or you find a reflection of it, but then a line search would allow you to find the global minimum from there. And this is a random system, so this theorem holds with high probability, right? So again, the model here was that the generator, this generative model, we're describing as an expansive Gaussian neural network. Now, we can discuss the merits of that model. A couple of comments are, if you look at real trained neural networks, including say like the famous AlexNet, which is what really birthed the modern movement of deep learning, then if you look at the statistics of the weights of those nets, then you do get like Gaussian-like structures in there. And so empirically there is Gaussian-like behavior. But also, like we're trying to make like a fundamental advance. We're trying to really show that these priors can be optimally exploited. And the first natural model to study is one that is random, as has been done in the field of compressed sensing for decades now. So all right, so this result, right? It's a non-convex optimization. It's saying that it guarantees that if you run a gradient descent, then you get to the global minimizer. And indeed, there's a follow-up paper that's been submitted which actually shows that gradient descent itself converges to the global minimizer if it's, you need to do some little tweaks to it, but you can like prove convergence of it. All right, so I do want to at least hit at like some of the like interesting math that's in that paper, right? So this is, really it comes down to concentration estimates of random matrices. And so what's really challenging about this is you end up having these matrices which depend on space, but they depend on space in a discontinuous way. So the source of this discontinuity is something called the RailU activations, right? So in deep learning, there, a neural network, it's a series of functions that are composed together, a linear layer and then a nonlinear layer, and then another linear layer, another nonlinear layer. That nonlinear layer is often something called RailU, which is literally take the max of your input with 0 component-wise. And so then now if you differentiate that, you have an indicator of whether your input is positive or negative, right? So that like the central, like the beating heart of like this, like this theorem that I showed you a sketch of on the previous slide was, how do you show that this sum of random rank 1 matrices, but also with these indicators present that depend on space in a discontinuous way, how do you show that this concentrates around its expectation reasonably? Right. So this is all, these are very much like Roman Vershinin style estimates of singular values of random matrices. And so now this lemma, this lemma is actually now outdated. There's been subsequent work that followed up on our work, which found better ways of actually like showing the probabilistic concentration that was needed. And I'll comment on that when we get to the references slide. Okay, so there was some theorem. So there was a theory that said that these deep generative priors could be optimally exploited. We can actually compare these like phase retrieval methods to existing, or sort of this compressive phase retrieval methods using deep phase retrieval, the second row, from other methods that are common in the literature. And indeed, with many fewer measurements, we can like extract the signal more accurately than these like standard methods. And we can also see that when we plot like error versus measurement count, it can be a very sizable difference between the performance using deep generative priors and sort of the best known sparse phase retrieval algorithms. Now, in this plot, you can see like indeed this blue curve, this deep phase retrieval curve has low reconstruction errors with many fewer measurements than the sparse phase retrieval ones. But you probably also noticed that the performance level of these like deep networks seems to level out and saturate, whereas the other methods, if you have enough measurements, like the error goes to 0. So I do want to comment on this because this gets at a big question related to these deep models. It's like, when can you trust them? And so one of the catch of these models is like there is representation error, right? You're modeling an image as being in the range of this trained generative network, but not everything is. So here, for example, like this first row is a bunch of images that are not of celebrities. And so then you take a neural network that's trained, that's a generative model for celebrities, and you say what image in the range of that generative network is closest to these images, right? And you can see, okay, well, it kind of does okay, but like this guy in the middle, his glasses and beard get removed by the model, but in a in a like meaningful way, right? And like it takes this like older lady on the right and then turns her into a younger lady. This is because of the bias in the training data set. So indeed, like these GANs, these generative models can have significant representation error. So now there are challenges. Like if you're going to use these generative models to recover your image, you need to make sure that your image is in the range of the GAN. Otherwise, you can't use it to model your image. So now the field has has made a lot of progress in this in this front over the last few years. Maybe you'll have to invite me back in person after COVID to talk about those. But I want to share so just some amusing things, and then a couple of thoughts, right? So in this problem, right, remember our goal was like we trained a generative model to describe the natural image manifold, and then we use it to recover other images. So now if I try to do out of distribution signal recovery, like I give it images that are off distribution, then what happens, right? Well, in some cases, these models are going to round to the nearest like person, right? So like here we can see like here in the second column, there's Heath Ledger, right? This model like turns that into what the model thinks like a human face looks like. Or this chimpanzee gets turned into this woman who happens to have sunglasses in exactly the same size as the eye sockets of the chimpanzee, right? So in a sense, these models are doing what we told them, right? They're saying, give me the closest human face to the image that you provided. So in that sense, they're being successful. But when we want to do imaging in the real world, we often are trying to image things that we haven't seen before. Think about the black hole from last year, or a new medical pathology. So we like need performance to be good off distribution. All right, so just to begin kind of like wrapping things up, so right, this talk was about like signal recovery under generative priors. The main theme was that generative priors can, in some cases, outperform sparsity priors for a variety of problems, and particularly imaging problems. Now, it's not going to be the case that all problems like generative priors will outperform sparsity priors. Like if you have a system which really is best described by sparsity, then it may be very difficult to beat that. But the reason why they could outperform is they can both provide tighter representations, meaning like the dimensionality of the representation could be lower. That is to say, the dimensionality of a nonlinear manifold describing a collection of images could be lower than the sparsity level of those images with respect to a wavelet basis. Finally, the generative priors can be optimally exploited in nonlinear problems where sparsity priors cannot. So we're getting this double whammy. Like not only could generative priors give you lower dimensional representations of your signal, it could be possible to exploit them at the dimensionality they have, as opposed to the square of that dimensionality in the case of sparsity. So now, of course, you get nothing for free. So what's the exchange? And so here, this low dimensional non-convex optimization is what you get instead of these like high dimensional convex approaches. And so generally speaking, we like convex methods because like any local minimizer is a global minimizer, and there's a lot of like carefully developed solvers for them. But when push comes to shove, we might prefer a non-convex method where we happen to not get stuck in local minima to a convex method which doesn't actually have the right sample complexity. All right, so and then to conclude with some thoughts, right? Now that we've like brought in deep learning into like inverse problems, there's a lot of questions that come up, right? Like the entire paradigm of what we talked about in this seminar was about generative modeling. And it said, right, learn the distribution of data and then exploit that distribution at inversion time. Well, there's an entire other class of methods called end-to-end training, which is to say, just build a neural network that just goes from your input to your output. And this is exactly how the whole field is built, right? You hand it, say, a bunch of images and a bunch of labels. This is a cat and this is a dog, and you just like tell it to learn the whole map in between. So generally speaking, right now, the best methods are end-to-end trained. And generative modeling hasn't quite beat those yet. So we talked about the issue of representation error and like bias you can get from training data. Like this is a major concern. There are approaches for this, some of which are very principled, some of which are ad hoc. but there's actually a ton of methods that are all like waiting to be analyzed for like in this domain. So then this third question of like how robust are neural network methods, there's some interesting like recent work that shows, you know, a variety of neural network methods for working on MRI. Actually, all of the methods miss a real medical pathology that's there, right? So what happens is they end up showing you a very pretty picture instead of the correct picture. And they don't necessarily tell you the amount of uncertainty they had, or they didn't tell you that uncertainty in a useful way, right? So we need to robustify these methods. We need to know where they're certain, where they're not certain. This is a major theme of research. And then finally, like when I think back to like what is, right, the prior, you know, so like the whole principle of this talk is that the sparsity prior might not be like the right thing to exploit. So what exactly are we replacing it with? So in essence, you know, these neural networks are a big black box. You know, they have a structure. How does that structure bias them toward natural images? Like this is largely an open question in the field. All right, so here are a bunch of references for related works. I know this is a major field that's like taken off over the last few years. If you're interested, I encourage you to look at the 2019 and 2020 NeurIPS workshops that I co-organized with Professor Reinhard Heckel at TUM in Munich. There are these 2 review articles that are lovely, and you know this work has been extended to, you know, many problems like spiked matrix recovery, demodulation, denoising. There's been a lot of work on these and related things. So hopefully, I guess I think that's probably a good place to stop for now.
Okay, thank you. Let's thank the speaker. Okay, so yeah, we shall open the floor for questions. There was already a question in the chat. So from Abbas Khalili, professor at McGill. So in the lemma, the technical lemma where you showed the deviation inequality, I guess, for discontinuous sum of random matrices. Yeah, so shouldn't you have a 1/n for the sum in the lemma?
Oh, sure, because let's see. Yeah, so there should, because the left term is really like the average of these, and so that should be like the expectation. Yes, there should be a 1/n there.
Okay. Actually, so also,
well, wait a minute. Is it, or are they tucked in? Yeah, well, yeah, I think yes. I mean, there's a lot of knobs that you can have, and how you scale the Gaussian random variables. But sure, let's just say there should be a 1/n there, and handle the scaling is appropriate.
Yeah. So also, by the way, since we're here, what norm you're using here?
In this case, this is a operator norm, so the largest singular value.
Okay, so induced by the L2 norm. Okay, great. So is there any question? Maybe you can just unmute yourself if you have a question, or use the chat.
I have a question, if I may. First of all, thanks for the beautiful talk. Super clear, very interesting. So I mean, I don't see how to remedy this problem that if you learn a certain distribution and then you're outside of the distribution, and I mean that this is ever going to be resolved. But why? I mean, we had been working here a little bit on maximum entropy on the mean, where you have a prior distribution. Say you learn your prior distribution, and then you actually optimize over distributions again, and it's completely unparameterized, and you basically want to find the distribution then that whose expected value gives you the minimal error. Do you see any benefit of maybe coupling these ideas?
So yeah, so I think this. So there, one way of dealing with this out of distribution problem is to make sure you have a model which has all images in distribution. For example, to maintain a probability distribution over all of image space. And there are various ways of representing that. And indeed, there have been a variety of, there have been some methods that have shown success with that. So for example, like there are something called like normalizing flow based neural networks, which maintain basically you can access the probability density function as the output of the normalizing flow, and then you can use those to literally maximize likelihood conditioned on the measurements. And so then that, like, if the measurements pull you off of that like high probability region, well, that's fine. You can make that trade-off. Now, but there are other approaches too. And so for example, one way of not being biased toward your training data is to literally not use any training data. And so there's an entire category of methods called like untrained neural networks, which take purely random neural nets, and then you optimize the weights of those neural nets to fit the measurements of your exact problem. So this actually works quite well. And what this is getting at is the actual architecture of the neural nets themselves. Like it prefers natural things in ways that are not fully understood at this point. Right. So those are two like totally different ways of getting out of this this issue. However, the analysis the analysis of both of those ways is subject to active research.
And I have another thing. It's more of a comment. I think you presented basically like the landscape for the the deep face retrieval, right? Yeah, I mean it's not. I mean it's not that non-convex, right? I mean it's a weakly convex function. That's what it looks like, right?
Well, yes. So this like one of the themes in so like signal recovery, the applied mathematics of signal recovery in the last decade or so has been that a lot of these non-convex approaches actually have shall we say are not that non-convex. And then if you have enough measurements, then sure there's some random noise in your data, but then the structure of that of the problem is favorable for gradient descent. So I mean, indeed, like this theorem, right? I mean, it's providing a guarantee based on these like expansive Gaussian networks. And so it's, if you are sufficiently expansive, then you do avoid all these spurious local minima, and sort of much like how in the proper phase retrieval literature that holds, say from like there's like this wording or flow method like shows something very similar in the dense phase retrieval case.
And so that's more a technical thing that I never can really quite wrap my head around. For example, in your compressive phase retrieval or deep phase retrieval, I mean, the objective function is clearly not differentiable because you have the absolute values inside. Do you just, does the code just ignore that, or?
Yeah, so this is what a computer scientist would call a differentiable function. I mean, mathematically, this is like almost everywhere differentiable. And so then with probability 1 with any initialization, then you're not gonna exactly hit, you're not gonna hit a point of non-differentiability. Now the theory,
usually the interesting points though are in points of non-differentiability. I mean, the simplest example would be like that, right? And then
yeah, so in this so in this case, like the interesting point is not a point of differentiability. Like the interesting point is x naught, which when you start like plopping down all these like random hyperplanes and partitioning space, they're not going to fall on the exact image you're trying to recover.
Okay.
So now that said, to do a proper analysis, I mean, it's easy for the computer scientist to say, oh, sure, it's never going to happen. Just code up your method. You're not going to hit it. So let's move on. But like mathematically in the theory, then yes, we do have to deal with those points of non-differentiability. And so technically, so like when I said like the method needs some tweaks, right? So one of those tweaks is it's actually a subgradient method instead of a gradient method. And then at each individual iteration, like you're computing a subgradient to that function. So now if you're at a differentiable point, then your subgradient equals your gradient. If you're at a non-differentiable point, then you could get the subgradient by moving infinitesimally far in any random direction, and then using the true gradient in that case. But literally speaking, the convergence proof that we prove is for a subgradient descent.
I have a
Congratulations,
question.
Paul.
Oh, sorry.
Yeah.
Oh, sorry. Go ahead.
I just
Adam?
want to say to Paul, congratulations, because Tim asks one version of that question to every single speaker, and that's the best answer that's been given so far.
Thank you.
Right, Tim? Do you agree?
I don't know if that was a dish on me or a compliment for Paul, but
It was trying to be both.
I agree.
And nice talk. Nice talk. I'd like to talk to you, but maybe I'll talk to you afterwards.
Yeah.
I've got a question. Thanks. On this slide, do you have Gaussianity assumption on Z in RK?
So when we think about where did G come from, G came from the modeling assumption that it is a function which maps a standard Gaussian into a sample of your distribution. So in that sense, the Gaussianicity is baked into G. That said, this model doesn't exactly exploit Gaussianicity. The reason for that is the range of G is a low dimensional manifold in image space. And so it's k dimensional. So if you give me k points, that pins down one, right? Like I don't need to leverage Gaussianicity in that case. Now, if you, and this goes back, to the question from before about like, if I maintained a high dimensional probability distribution over all of space, right, then I would need to exploit that Gaussianicity. Like I would need to then prefer among the infinity of solutions, the ones with the highest probability. So really, it really depends on like the exact nature of G.
And then that would be like the exact nature of G. Is it going to be application dependent or like?
Well, so I would think of it as, so what the holy grail here is, like, if we can get these generative models to be state of the art, right? So then someone like someone who's experienced at training neural nets would go take a bunch of MRI images, build AG, and just be like, here you go. Here's the model for MRI images. And then now a domain scientist doesn't have to know that. They just plug that in to they choose the objective they want to minimize and have some optimization problem solve it.
Okay.
So now if you're asking like, what generative model is actually most likely to work for this? I mean, there are a variety of methods out there, right? So there's like some methods like maintain low dimensional manifolds. Some methods maintain like probability distributions over all space. Some methods literally maintain like explicitly like the log gradient of the log of the probability. And then in order to sample from them, you have to like sample some Langevin dynamics. So like these are roughly, this field is the more expensive the model, the better the results you have. So it's all a trade-off of how much you're willing to wait to get that output. If I were to say, where I really think like the exciting modeling area is now, I actually think it's not related to learning. I think it's these untrained methods, like that the neural net architecture itself is biased toward natural images. Now this is getting toward a more fundamental mathematical question. Like what class of functions do neural networks like? As opposed to the questions that I don't like answering, which is, what does natural data look like, right? How is a cat different from a dog? Like, I don't know that. But if you say, how does this expansive Gaussian model, like what images is in its range, that I understand. Right. So I think like the challenge with the field of deep learning is, right, it's such an empirically driven field, and its entire success was based on just like raw performance metrics on image classification in particular. And so like we need to start understanding the theory behind it, right? We need to get more mathematicians, into this field, but it's really not clear what exactly they should be proving.
Okay, so maybe
thanks.
Yeah, there was another question from the chat, and so I'll ask that, and then probably I'll let people go, and of course we can, whoever's interested, like can stay here for discussion. And also, Paul, what's the time frame? That also we don't want to.
I mean, I have time. I've
okay, cool.
No
Yeah, because also have more questions, but I don't want to oblige everyone to stick around for hours. So, okay, for now we have a question from Dashyant. Does the type of neural network for deep generative model used affect convexity?
So I would say yes, in that they're all not convex.
Yeah.
I mean, there are such things as like convex neural networks, but the competitive models for outputting real samples that are photorealistic, et cetera, like these are all non-convex.
Okay, so if there's no other official question, maybe we can pause the recording and keep chatting. I don't know, people starting leaving.